To solve an initial value problem using the Euler's method. So we have this graph. We have the solution curve and the tangent line. The solution curve shows the differential equation, while the tangent line shows the Euler's method's approximation. The Euler's method uses the formula yn plus 1 equals yn plus h times f bracket xn times yn. So here we have the Euler's method, and this is the initial value 0 and the final value of x where we have to find. So using the initial condition x equals 0, y equals 1, we will sub out and we will calculate. So after calculation, I got 1.008, and this is just the first step, so we will repeat this step until we find our desired answer. So let's show this in Excel. So it should look a bit something like this in Excel. So for this column, I use the formula like this. And for this one, it's a different formula because okay, so for the step size, if I were to change the step size to 0.5, you auto calculate to about the same value. So if I calculate backwards, this formula calculates it by adding 0.2 constantly until we get our desired number, which is this. This was the answer I got just now previously, 1.008. Now let's use this, compare this to the actual formula, which is this. So firstly, we separate the variables, y to one side, x to one side, and then we integrate both sides into this, Then we solve for y. Cancel, you should get something like this, y equals 2x. Now the initial condition which I mentioned previously, y equals 1, we will sub out y for 1, and then we will get something like this again. No, this. So after we finally sub c into the equation, we should get something like this. So now we solve for the last part. Solve y bracket 1 for this. Once we sub in, we should get something like 1.2909. At x equals 1, y1 equals 1.2909. While using the Euler's method just now, we got 1.2244, which is this one. So the error of this is about 0.0665. This error corresponds to this curve. Reducing the step sizes reduces this error. So if you were to reduce step size, this error will be reduced. So in conclusion, we use the Euler's method to solve a differential equation automated in Excel and compare the results with the exact solution. The Euler's method is effective for numerical approximations. Thank you for watching.